Recording in progress.
Hi everyone, my name is Thomas and I'm a fellow student in the modeling class that you're in that meets on Mondays. And a little bit about me, this is my third semester in the business analytics program. I actually did my undergraduate here at UT Dallas in business administration, and I did a fast track program. So this is my fifth year at UTD, but the last 2 semesters have been mostly graduate school. And so when I'm talking with my group and I'm talking to some of the people in class, this looks to be a lot of people's first ever semester in the business analytics program. And when it comes to the concept of regressions and when it comes to running some of these models, there's a bit of confusion and a bit of trial by fire that is, I think, occurring in the classroom. And so I you will take courses. Your statistics course will cover a lot of the statistical concepts. Your econometrics course is an entire course strictly over regressions. If you ever take analytics with R, that'll go more in depth. But I want to discuss with you some of the math behind what you're looking at when you look at something like this, which was the predicting apple taste based off of these variables that we did in class. I saw a lot of confusion, and I remember, and I've been talking with my group, and it's and so my job is to explain to you what this is and what it looks like. And so bear with me. I just want to say at the outset, I'm not a phenomenal student. It is more by virtue of taking several classes that I understand this stuff. A lot of the high level statistics and the deep math is, not my forte, but I figured I'd give it a shot because I think it'd be really helpful. So this will be maybe 15 minutes. I'm hoping to keep it close to 15 and not 20 or more. But let's explain what we're actually looking at. But let's first take a step back and talk about what a regression is. So what you could look at is we're going to use the example of predicting the price of a house. And so a regression is simply put a way to predict something. In this case, apple taste. But we're going to be looking at predicting the price of a house. And we're going to start with by square feet, predicting the price of a house by the square feet of a house. So you could let's say you have this data set and it's got a number of houses and it's got their square feet and their prices, and you could plot it in a scatter plot and see, oh, it looks like houses with more square feet are then, more expensive. And the regression is the goal of the regression is to tell you how much more expensive. If you see me looking like this, I'm looking at kind of my notes. So just so you know. But so the problem you run into without using math is you might think that it looks like this. Your friend might think that it looks like this. Your other friend might think it looks like that. Your boss might think it looks like that. That this relationship looks certain ways. And so what I mean when I say that is the slope of this line, let's say it's 30. You are then saying that for every 1 square foot increase in house size, there's a $30 increase in price. And so that's what we are looking for, is we're looking for that golden number of what is the relationship. It might be 50. That's an awful 5. It might be 50, it might be 3. We don't know. And so we use the computer to figure it out. And what the computer does is it calculates a method of finding the line that is as close to as many points as possible. This is called ordinary least squares. And so what it does is it draws a bunch of lines. We're just going to draw one, and it says, yeah, we could go through. What is that? That's our line. We'll use this line as an example, and and then it calculates from each of these lines what's called the residuals. And so a residual is the difference between, this is our predicted, for a square feet, say this is, 100,000 square feet. We have a predicted value of, let's say, $150,000, right? That's how much we would predict with whatever this line we drew. But we have an actual house that sold for $140,000, right? And so the residual here is 10 because we guessed $10 more than there actually was. Residual here would be like, let's say, -15. The residual here would be massive. It'd be, maybe $50,000 off, -$50,000 off. So it does all of these residuals. It squares them, so it multiplies them by themselves so that these negative signs go away. And it figures out the line that has the least residuals, the least amount of residuals on average. The computer does this. You can do this by hand, but it gets really painful. And it puts that into and it gives you that output. I don't know why it's not clearing out that last red thing, but it gives you this output. And this output is in a very specific form. It says that your y value is equal to, in econometrics, you will learn this as a beta value or a b value, predicted beta. But we'll just say a slope times an x value plus a constant. This is going to be, because you might say no house ever sells for below $100,000. This house might, but on average, no house is going to sell for below $100,000. The computer figures this out. Great. So that's something that's complicated but manageable by hand. But what we are dealing with is data sets that will have 10, 15, 20 more, with big data, even way more X values, way more X values, way more predictors, way more variables. And it becomes very not helpful to draw an n-dimensional graph. Like you could maybe get a third dimension and put a z-axis here, but after that, it becomes really hard for a human to visualize and honestly kind of pointless. I wouldn't think about it as trying to draw a line through however many dimensions. Just think about it as computer magic and learn what the numbers mean, because that's what you actually care about. But this equation stops being y equals slope of x plus a constant and starts being slope 1 of x1 plus the slope 2 of x2 plus the slope 3 of x3 plus, right? And you might think, plus c, 20 slopes and x's. And so it becomes impossible to calculate by hand. It becomes impossible to kind of visualize all of these residuals. And so we let the computer do the work and we interpret it. And so you'll start to see things where it's like, we'll see this in just a minute, so it's a little bit of a spoiler, but like, let's say this one is your square feet, and this one is the number of rooms in the house. Well, having an additional bedroom, or like the number of bedrooms, right? And having an additional bedroom is going to increase the square feet. If you picture a 2-bedroom house versus a 5-bedroom house, a 5-bedroom house is going to have naturally a much larger square feet. So if you ran a model that did not have the amount of rooms, you're going to get one slope for beta 1. But if you ran a model that did have the number of rooms, you're going to get a different slope for beta 1 because there's a relationship here. And so that's complicated. And in econometrics, you'll go over how to figure that out. We might go over that a little bit in this class, but that's really econometrics. So don't worry about that too much, but you'll see these betas change as you add in more variables is kind of the takeaway from that. Okay, so let's finally make our way over from this world of theory to an actual problem that we can sink our teeth into. And that is going to be this problem. I loaded in a data set that I did from my econometrics class that has the price of houses, the square feet of houses, beds, number of beds, number of baths, the age, the stories, and whether or not the house is vacant. It's got couple, not a ton of rows. It's got, 800 rows, 900 rows, maybe 1,000 rows. Okay. And we ran a linear regression. All of this code is from class. I'll show you it if you really want to see it. But all of this code is copy and pasted from class. And it's, you read in the thing, you add in a constant. Other programs, if you do a regression in R, it'll automatically give you a constant as an intercept. Python does not do that. So you have to add in this constant variable. So you'll see it's always 1 over here. And then you're going to say, this is my Y variable. And we're going to do one simple one so I can explain what these numbers mean. And then we'll show you with everything in the data set. So you're immediately looking at linear regression 1. You say, oh, it's ordinary least squares. We're trying to figure out price. The ordinary least squares, OLS, least squared. So that just means we're trying to get the least squared residuals. Okay. Well, we're going to start with square feet. The golden number is the coefficient. That is the actual relationship between square feet and price. That is the slope of this line. And so what we find is that slope is 81. Each 1 square foot increases the price of the house by $81. Something like that. This is gonna, depends on the scale of your graph, but it's gonna go up. So $81. The other thing, I'm going to go in order. I'm going to explain these in order of the amount you should care about them, not in the order of them appearing on the screen. The big one you should care about is the p-value. This is what's called the p-value, I'm not going to spell out value. I'm going to spell out value and it's going to look up. Okay. The p-value is the probability that this number is significant. And so there's math behind how you get to a p-value. It's, the probability it's greater than t, and we're going to, you'll learn that in your statistics class. Right now, all you need to know is this is a probability that this is significant. And so this has a very high probability. It's effectively 100% chance it's significant because there's a less than 0.1% chance it's not significant. If we go over to oh my goodness, can I not go over to apple tasting? Great. We go over here, this one has a 89% chance that it isn't significant. Over in the apple tasting sodium, it is very non-significant. So you want this number to be low. You want this number to be as low as possible. Sometimes as high as 0.1 is acceptable. 10%, you're 90% confident that this value is, and this variable actually matters and is different from 0. But it's a difference if you're measuring whether or not someone's going to go to McDonald's on one given day. You'll go with a 90%. if you're measuring whether or not an airplane is going to crash, you might want a 0.00000000001 over here on significance. And so both of these are very significant. And you'll see that the square foot constant, that the constant is negative here, which is really interesting. I wouldn't worry about it too much, but yeah, if you're like me, you probably do. But if you think about it, right? If you think about square feet and you think about like this is your price, this is going to be your square feet. And then this is going to be, 0 on your price. You're looking at a normal graph. This is going to be your center, 0 price. Your data points, like we said, you're probably not going to sell a house for less than $100,000, and you're probably going to not sell a house for less than, I don't know square feet of houses. I don't know, 2,000 square feet. It seems accurate. Yeah, 2,000 square feet, right? So all of your data points are going to be up here. And so one way to do this, if the computer could do this, would be to say, all right, we're going to start at 100,000 and give you this really shallow slope. We're going to give you this slope right here, and that's going to get you pretty accurate. But the other way to do this would be to say, we're going to start at negative whatever and give you a really steep slope. And the computer found out that doing this negative and this steep slope minimized the residuals. And so this is our best model. It's very significant. Okay. So that's our coefficients and our p-values. Your t-value is linked to your p-value. It is kind of a measure of the standard error, which we're about to get to. So the standard error is you're guessing a specific slope. In this case, it's 81, right? But the computer's telling you, we think it's 81, but we're 95% certain. Well, we know it's 81, but we're 95% certain it's between about maybe 77. That's maybe a bit, maybe 77 and maybe 85. We think it's 81. 81's our best guess, but we're 95% certain it's between those two numbers. And the t-value is kind of a measure of the difference between these. Because if you think about it, let's say you do something and you get a slope of 1 with a standard error of 5. Well, that's awful. That's not really good. The standard error is so big that you're not actually getting meaningful information. But if you get a slope of 1,000 with a standard error of 5, the standard error is so small relative to the size of the numbers you're predicting and the variation you're trying to predict, that's actually an absurdly low standard error, right? So you can see, so the t-value is this number and it's in a bell curve and you want to guess the probability of that number showing up and blah, 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 blah. You'll learn all of that in statistics. I'm not even the right person to ask about all of that statistics, but you'll learn that in statistics, but it's kind of a measure, a t-value that is further from 0 is a better t-value, but I would just ignore this and focus on this. Standard error, like I said, is that, and you might be wondering where did he get 77 and 85 from? It's that. So this is literally just the coefficient plus the standard error and minus the standard error. So it's 2.5% on either side, 95% in the middle there. And the big thing is if this contains 0, if the guesses of the slope contain 0, you're going to get a non-significant p-value and it's going to say, no, this is a bad this is a bad model. So if we actually take a look back at the if we take a look back at the, I'm sorry, I'm trying to get back over to mouse. If we take a look back here, we see that all of these contain 0 between -1, and then high p-value and a t-value that's close to 0. High standard error relative to the coefficient. Okay, great. So that's all of this nonsense. Now let's finally talk about how to tell if the model overall is any good. And that's going to be all focused in this R squared value, that in this R squared value right here, and the adjusted R squared. So the R squared is a measure of how much of the variation in Y is explained by the information you give the model. And so if we go back here, there is, some amount of variation in Y, anywhere between this value, between this value and this value, there's variation, right? And so if we condensed all these, if you just looked at Y as a thing, it'd get a lot denser here. There'd be a couple of outliers there. And so you get all this variation. And your R squared value is like how much of this is explained by adding in this square foot dimension and making this. And it's like, it's pretty reasonably explained. It definitely gets higher, but you have these outliers here, and it's not, it's not it's not fantastic, but it's pretty good. And so what we actually found out, it's a lot easier to draw these dots than it is to get rid of them. What we actually found out was that this one, 67% of the variation in Y can be explained by X. And in some cases, that's really good. In some cases, that's really bad. It's all model dependent. What the adjusted R squared does is it penalizes you for each additional variable you add to the model. So let's take selling your car as an example. If I told you, if you give me 5 pieces of information about your car, I can give you an 80% accurate guess of how much your car is going to sell for. This is what Kelley Blue Book does. You take some make, model, the make and model of the car, the year of the car, the amount of miles the car has on it, and it takes the condition the car is in and says, we're pretty sure you could get it between this amount and this amount. Great. 5 pieces of information, 80% accurate. You're like, that's pretty good. Now, what if I told you, if you bring the car into the shop and I do a 500-point inspection on the car, I'll give you a 99.999% accurate evaluation of the car. You'll be like, that sounds great. Like, that sounds pretty good, Like, that's way more accurate. Sure, you have to take the 500-point inspection, but I'd be willing to do that for 99.999% accuracy. What if I told you, you give me a car, I'll do a 500-point inspection, I'll give you an 83% accurate adjustment of the car. You'd say that's stupid. I would never do that. Because I could just give the guy the 5-point and I don't care about the 3-point. So that's what the adjusted R squared tries to do, is the more variables you give it, the adjusted R squared is always going to be lower than the R squared. The more variables you give it, the harder it is to get a good adjusted R squared. If you give it a bunch of good variables, the adjusted R squared might go up. If I'd say 5, I'll give you a 80% accurate. You give me a 6th piece of information, tell me whether or not it's been any wrecks, I'll give you a 90% accurate. Well, that's a pretty good thing. You'd want to do that. So that's the stuff you need to worry about. Don't worry about F statistic. Don't worry about that. Don't worry about the log. Don't worry about the AIC, BIC. Really don't worry about the AIC, BIC. That's the area econometrics. Don't worry about any of that. Don't worry about any of this. I don't even know what half of this stuff means. So you're really just concerned about the coefficient, about variable, coefficient, p-value, r squared, and adjusted r squared. That's what you need to be worried about. So let's run it on the full model. I know this is getting long. I'm really sorry. But on the full model, you'll see we added in a bunch of extra things. And we've got square feet actually is more and still significant. Beds is actually less. We'll get to that in a second. Baths is actually less, but it's not significant. We have no reason to suspect. This is saying for each additional bath, the value of the home lowers by $1,000. But we have no reason to suspect that that actually is any different from $0. And what you mean by that is if we took if we had, if we had this guy, we have a reason to suspect that the slope of this line is different from exists, and it's there. If you have a different data set, you might have a negative slope, but it looks reasonable. If you had data that very clearly had no relationship, the slope of the regression line that minimizes the least squares regressions would be zero. It would be a zero sloped line. And so what you're saying by having a non-important regressor is we have no reason to believe that this is any different than zero statistically. Okay. Age of the house decreases by 300 years is significant. Stories decreases by $6,000. Maybe significant, maybe not. Vacancy is significant, and then the constant is now positive, which is really nice and more in line with what we'd actually expect to see. And then the r squared is up, and the adjusted r squared is also up. So what this model is telling us is by adding in these 6 extra variables, it's still a better model. We're predicting the price a lot better. And so if I told you I had a 10,000 square foot house with 3 beds, 2 baths, 20 years old, 2 stories that wasn't vacant, you would say, okay, 20,000 times 96 minus this number times the 4 beds, minus this number times the 24 years, or this number times the number of baths, this number times 24 years, this number times the number of stories, and you'd be able to get your guess for what the price of the house was, etc., etc. And so just because it's important to hear, like, I live in a 100 square foot about bedroom, about a 10 foot by 10 foot bedroom. That's where you see me. And yeah, so that means it would be 100 times 96 more dollars minus 17,000? Minus $17,000 times 1, and so you're getting kind of it's a balancing act between bedrooms, right? If you buy a house that's a tiny house and has 8 bedrooms and no living room, probably wouldn't want to buy that house. But it's kind of implying this relationship here, and you just kind of have to guess on that. The last thing I want to talk about, I said I know it's getting low, is this vacancy. Because if you look at the data, vacant is either a 1 or a 0, right? And so if we think about our equation, y equals beta 1 x1, let's say that's that's our $96, right? So it'd be y equals 96 square feet. And then you do, minus that times bed, minus that times bed, whatever. it would be minus 9895 times this variable of whether or not it's vacant. And if it's a 0, that all goes away because it's multiplied by 0 and you just get square feet. If it's a 1, that stays. So if we have this slope, this is a one-time detriment to the slope. So you're pretty much saying any house that's actually vacant, the slope's going to look like it's going to have the same slope, but it's just going to be lower. And that's how kind of dummy variables work in impact models. This was longer than I wanted it to be. I'm really sorry. I really wanted to keep it at 20 minutes and now it's 30. But it's also really late and I don't really have time to do it again. I don't want to put a 30-minute video on your plate, but it's also super information dense. I need to get working on this homework. I've got work tomorrow morning. Yeah, so good luck. I hope this explained some regressions. This is an entire econometrics class and statistics class condensed into 30 minutes. So please, a little grace at the amount of time. And yeah, I've been Thomas. I hope this helped a little bit, and good luck, y'all. It sounds like it's going to be a pretty steep class. Expecting you to know regressions and know Python is a lot. Yeah, but I hate to say it, I don't want to say this level is par for the course for masters. I'm soapboxing a little bit, but the amount of work like that this homework is pretty par for the course for your master's courses, and it's steep and rough, but we're here to learn and hopefully do that together. We're on this together, but good luck to y'all. I hope your groups are finding the assignment easier than mine is. And I hope you all understand eigenvalues better than I do. Thank you very much. And yeah, I don't know, I'm gonna work on homework or something.